Okay, good people. I'm going to continue the last video. I got kind of cut off in the middle of the variation parameters. Let's just go. Let's just recap. We started with this differential equation. We did our Bernoulli tricks, and we got to u prime plus x plus 2 over x times u equals 3 e to the negative x. Very nice first order linear differential equation, and we're going to solve it with variation of parameters. Then later we're going to solve it with integrating factors. So we started to say that u prime plus. So what we did is we took the corresponding homogeneous version. And by the way, I'm so sorry that the word homogeneous is used in two different contexts. Usually we're going to use it to mean that I have a zero over here. That's usually what homogeneous is going to mean. But we saw in class that it also could mean a differential equation where you always have y over x. So the word homogeneous is used in more than one context. That makes it more confusing. So I'm also confused. Welcome to the club. Meanwhile, we solve this equation. This is when we set that equal to 0, we get a very nice separable differential equation. The integral of du over u1, I'm just going through the steps here. Ln u1 equals negative x minus 2 ln x. So u1 is equal to e to the negative x, e to the negative 2 ln x. And u1, finally, u1, which is the specific solution, a specific solution of the homogeneous corresponding homogeneous equation, comes out to be x to the negative 2 times e to the negative x. And this is really where I got up to at the end of the last video. So now what we want to do is we want to say that u, the solution to this differential equation, u is equal to v, which we want to find a v, times u1. And u prime is going to be v prime u1 plus v u1 prime. Now we know that u is equal to v times u1, but u1 is x to the negative 2 e to the negative x. So u is this, and u prime is, well, it's a little messy, it's going to be v prime x to the negative 2 e to the negative x plus v times this derivative, which I need a product rule here, negative 2 x to the negative 3 e to the negative x minus x to the negative 2 e to the negative x. And just cleaning it up a little bit, u prime is equal to v prime, or rewriting it a little bit, u prime is equal to v prime over x squared e to the x, and e to the positive x, minus v times 2 over x to the third e to the x plus 1 over x squared e to the x. I'm just kind of rewriting and getting rid of all the negative exponents. Don't even ask me why. And now I just take these two guys over here and combine them into one fraction. So it's v prime. So u prime is equal to v prime over this minus v times that big fraction. Now I continue my variation of parameters magic, and I go here, and I'm going to substitute back into the original differential equation, the non-homogeneous differential equation. So I stick in v prime is this plus x plus 2 over x times v, and so this is v prime, and that's that, and I get these things cancel, and I get v prime over x squared e to the x equals 3 over e to the x. The e to the x's cancel, and I get v prime is equal to 3x squared, the first first easy thing we actually got. And then v equals x cubed plus c, a constant. U is equal to x cubed plus c over x squared e to the x, which is equal to y to the negative 1/3. Where did this big fraction come for u? Because u is equal to v times u1, and u1 was this right here, which is just 1 over x squared e to the x, and it just wound up here. I wrote it on the, instead of writing with negative exponents here, I wrote it on the bottom. So u is equal to x to the third plus c over x squared e to the x. But we're not looking to solve for u. We don't even know u. There was no u in the original problem, so we have to convert it. We have to back substitute, convert it back to y. U is equal to y to the negative 1/3 power, so therefore I have to raise this to the negative third power, not the negative 1/3, but the negative third power. And I'm just going to leave it like this: x squared e to the x over x cubed plus c to the positive third power. Instead of raising it to the negative third, I raised it to the positive third and just flipped the fraction. And this is the final answer I get with this method. My next video is going to be solving this same differential equation, but using integrating factor instead of variation of parameters. I don't have to do it, but I just want to show you that both ways work.